am Sanya Kuller and this is Cute Little Yangshi, and in this video we're going to talk about how can you tell if two random variables are independent. That is, are A and B independent? So to find that, we need to find the probability of A and B happening and see if that is equal to the probability of A multiplied by the probability of B for all values of A and B. So here, what if A and B are Boolean random variables here? How do you calculate? Like A is true, A is false, B is true, B is false. So how can we determine if A and B are independent? So we're going to be doing that in this video here. That is, we're going to be given the situation that given this joint probability table, is A independent of B? And that's the same thing as asking are A and B independent, or is B independent of A? So how do we go about doing that? Especially even more so now that we have a third random variable C that's in the mix. So how do we do that? That's what I'm going to talk to you guys about today. And little Yangshi will too. Go stats, go stats. So basically, if A and B are independent, then what we would say is that if A is independent of B, then the probability of A and B is just the probability of A multiplied by the probability of B. So now all we're saying is A independent of B given the value of C? So all we have to do is to each of these probabilities, we just need to add the given C part. So we take the same idea here that you see here, and all we're going to do, so if we wanted to see if A and B were independent, then the probability of A and B is equal to the probability of A multiplied by the probability of B for all possible values of A and B. So because they're Boolean random variables and they're basically like events, A and B, they could be true or false. Like boo liar, they could be true or false here. So basically, A could be false and B false, A false and B true, C true and B false, or both of them could be true. So we need to consider all four of these possible outcomes for A and B and test all four of them. And if even one of these tests fails, then A and B would not be independent. So sometimes when you're doing these tests and you're calculating it by hand, to see if A and B are independent, calculating out this formula, then it can take a while to show, okay, I'm testing if both are false, if this holds, testing if A is false, if B is true, like, testing one by one by one. But if one of these fails, then you can just say that A and B are not independent, and then you can be done. So sometimes you might even just want A and B to not be independent. So because you might just be spared from testing all of these out. But I like numbers. I like having to do these calculations. That's why I majored in math and took up a lot of courses in math as well, because I don't mind this. I find it kind of nice. But you might just find it very tedious to go through all of these. And I'm going to just enumerate what all of these are. So if we want to test this out, for all four values, so if A is false and B is false, then the probability that both of them are false here, if we need to see if it equals the probability that A is false multiplied by the probability B is false. So basically we're taking this equation and we're putting in the specific values of A and B in there and seeing if the equation holds for all four of these possibilities. So like for instance here, so for A is false and B is true, we need to test that the probability that A is false and B is true is equal to the probability that A is false multiplied by the probability B is true. And then here, the probability that A is true and B is false needs to equal probability A is true multiplied by probability B is false. And lastly, the probability A is true and B is true need to equal the probabilities A is true multiplied by the probability B is true. So if A and B are truly independent, all four of these conditions, they need to be true. If even one again fails, like if we find, for instance, that this is not true, then we have to say, A and B are actually not independent. So we have to test all of them, and that's what I meant, that sometimes you can just be spared all of them. Or maybe maybe all of these are true till you go to the last one and then you find that they're not independent anyways, but you had to do all the math. So it is what it is. But again, yeah, all four of these need to be true. So yeah, this is just listing out like all four of these statements that need to be true. Like that means that, this probability on the left needs to equal this multiplied probability on the right for all these possibilities. And if all four of these are true, then A is independent of B, which again is the same thing as saying that B is independent of A. But if one of them fails, or more than one of them, or maybe all four of them are, true, just at least one of them needs to fail for A to not be independent of B. Or the same thing as, B not being independent of A. Now I have quite a little gang. I have Tuggle. Tuggle! Aww, there's a little Tuggle here. Here's Tuggle. Ooh. And there's me. So I'll just show them 1 second. They're very, very cute. Hi, Tuggle. Hi. Wow. They're very cute. You can see them there. But anyways, they also want to eat, pun intended, they also want to learn about probability. Right, guys? Okay, so yes. So anyways, next what we want to do is we want to find the probabilities for A and B as well. So we want to find A being true and B being true. Remember there were 4 outcomes. Tuggle, no. Okay, he's still there. The 4 values, A can be true, B can be true, A can be true, B can be false, A can be false, B can be false, and both of them can also be such that A is false and B is true, or both of them can be false here. So these are the 4 outcomes here. So what we're going to see here is that it's easier because we were sorting it on C being true or C being false. You can do it either way. So I just wanted to group them together based on A and B values falling together in these categories as well, of like so for like A and B, the values could be like true. This is like a truth table. I remember learning it in geometry class in high school, and true, true. Or I will follow actually how they did it here. Oh, we can do it either way, but let's sort of follow how I did it here. So the values could be like false and false. They could be true and false. They could be false and true. Or just true and true. So there are many ways you could write this truth table here, but because I organized it, this is how it looks here. So now if we're looking for the probability A is true and B is true, so both are true, then we're going to just see that I've grouped them together, and the only key difference between these 2 rows is just the outcome of C. So C can be true or false. True is and false is, so it doesn't matter. So what we see here is that we're just going to take this 0.2 that we have here and this 0 and then just add them up to get 0.2. So that's how we get this value here, 0.2, 20%. And what we see, and so since these are all 4 possible outcomes for A and B, they should add up to 1 in the end. Like that is what they should add up to. They should add up to 1. So that's what we see here. And then now we want to see probability A is true and B is false. So A is true and B is false. So that will give this to us here. A is true and B is false. That'll be like 0.2 plus 0. So that's what we have here, which is 0.2. And then what we want to do is we want to see probability A is false and B is false, so both of them are false. So what we were going to do here is we're going to say, okay, both are false. So that's just the top one, false and false. And you see that C can be true or false here. And that's what we get here, which is 0 plus 0.3, which is just 0.3. And last but not least, we see that the remaining unshaded parts here are for A is false and B is true, and C can be true or false. So that will be 0.3 plus 0, which is 0.3. And now if we add all of these up together, we have 0.2 plus 0.2, which is 0.4 plus 0.3, 0.7 plus 0.3 is 1. So this adds up to 1, which is great. Yay, we won! Please note that all the probabilities that we have gathered. So we know that the probability A is true and B is true is 20%. The probability A is true and B is false is 20%. The probability A is false and B is false is 30%. And the probability A is false and B is true is 30%. And if we add these all up together, they add up to 1. With this analysis, we also need to find the probability of A being true or false. So if we want to find the probability of A being true or false, we have to sort this table here. So I just sorted it, for the false values of A on top and the true values of A below. And then what I did is, so after I sorted it, I just kind of was adding up and seeing, he's playing with lights, how the probability that A is false is just given to me by these rows here. So probability of A is false is given to me by this. So I just added up the 0, and then the 0.3, and then the 0.3 again, and then the 0, and then that gives me 0.6. So probability A is false is 0.6, 60%. And then for the probability that A is true, I just kind of added up these rows where A is true, right here. And then again, the other one is. So for this one, I just added up the probabilities of A being true, which is the 0.2 plus the 0.2 plus the 0 plus the 0, which is 0.4. So the probability that A is true is 40%. So, and as we can verify, these add up to 1, which is good. And similarly, if we want to find the probability of B being true or false, what we have to do is we just said the probability that B is false or true. We just have to sort this original table now instead on B. So you can see the sorting on B here. Then we just kind of partition by the false and the true. So for B being false, there are these 4 out of 8 outcomes here. So half of them should have B is false, half of them should have B is true. So 4 outcomes for B is false, 4 outcomes for B is true here if there are 8 outcomes. So here, and this is because we have like 3 random variables here. So probability B is false, then similarly again will be given by, kind of controlling when B is false, which are these first 4 rows. That's what this is here. So that is just going to be this 0 plus the 0.2 plus the 0.3 plus the 0, which is 0.5. So the probability B is false is 50%. Then similarly for the probability that B is true, we just kind of control for when B is true here. And then that just gives us the 30% plus a 20% plus 0, which is 50%. So 50-50 chance, and these add up to 1, which is great. So 50% chance that B is false, 50% chance that B is true. Equally likely in this case. So now this is a formula cheat sheet. So again, we have these probabilities I just mentioned, and they add up to 1 here. These also add up to 1, and these also add up to 1. So now we just added in the probability A is false is 60%, A is true is 40%, probability B is false is 50%, and the probability B is true is 50%. It's all just a matter of speak. So, as cute little Yangshi would say, it's all just a matter of meow. Meows, I don't know if they're the same or not, but it's just a matter of speak overall. So basically, if all four of these statements are true, then A is independent of B, or equivalently B is independent of A, or just in general, A and B are independent. So the first is saying that the probability A is false and B is false needs to be equal to the probability that A is false multiplied by the probability B is false. That's the first test. The second test is that the probability A is false and B is true equals the probability A is false times the probability B is true. So basically, whatever is inside the and, that's kind of like what you are conditioning on in a way. So if in this case, if A is false, then you have to multiply by the probability A is false here. And if B is true here, then you have to multiply by the probability B is true. So that's how it works. So the probability A is true and B is false should be equal to the probability that A is true multiplied by the probability that B is false. So again, the same idea here, that these should be the same. And then lastly, the probability A and B are true, so A is true and B is true, should be equal to the probability A is true multiplied by the probability B is true. So all four of these, all four need to be true for A to be independent of B. All four. Otherwise, A is not independent of B, and same thing as saying that B is not independent of A. So A and B would not be independent if even one of these failed. So these are the four tests. You can do them in any order. This is just the order that I'm going to be testing them in. So the order doesn't really matter. But the idea is that if even one of these fails, you can just stop and you don't have to proceed. If let's say that this one failed, for instance. If this one failed, you don't have to go on and do the second, third, and fourth tests here. Or let's say the first one passed. Let's say that the first one passed, for instance. Then let's say the second one failed. Let's say that this statement was not true. Let me just kind of revision it. Then what you'd have to do is you just have to kind of stop right here. You don't need to do the third and the fourth. You can just say A and B are not independent. You know, if it fails, you do the first one, you did the second one did not work. There's no need for you to do the others. You know, this one did not pass. Or let's say that this one did pass. Then, you know, you can just go on to the third one here. So if this one passed, if this one passed over here, then you can sort of say, okay, this one passed, but let's say the third one failed. Then you kind of evaluated the first three anyways, but you just don't have to do the last one. You can just be done and say that A and B are not independent then. So you have to check all four. If we get down here, which is kind of a little annoying, but let's say that it happened to pass, you know, the luck of the draw, it happened to pass all of these but fail this, then you'd still say that A and B are not independent. It's just that you kind of had to go through all of these just to see that. You know, and imagine if this was the first one you had tested, then you didn't have to go through the others. So you just go through them in whatever order you want. This is the order I'm doing in this example. And if it keeps passing, you go on to the next one that you have, and the next one, and the next one, until you evaluate all four of them. And if it fails even one, then you can just say that you're done and A is not independent of B. But if you want to go above, you can just try out all of them though. So again, yeah, now we don't know if all of these will pass or not. So there's a question mark because we don't know if there's equality here or not. That's what we're going to figure out. That's what we have to figure out, Yangshi. Is there equality or not? So the first test, the probability A is false and B is false, is it equal to the probability A is false multiplied by the probability B is false? So that is, again, you know, according to the rule, like this is B is false, this is B is false is here. This is A is false here, and then this is A is false. So we use the formula sheet that we kind of had created, and from that, we find that the probability A is false and B is false is 30%. And the probability A is false is 60%. and the probability B is false is 50%. So what we can see here is that the probability A is false and B is false is equal to 0.6 times 0.5. Is it the same? So this is 30% right here. But if we evaluate this 0.6 times this 0.5, we get 0.3. So they are equal to each other. 0.3 on this left side, which is what this is, equals the 0.3 on the right side. So there is equality. 30% is 30%. So please note that the probability A is false and B is false is here equal to the probability A is false multiplied by the probability B is false. So the first test was passed. So the independence of A and B is upheld so far. So thus we can say that A and B are independent so far. The first test was passed. So the second test is the probability A is false and B is true. Is that equal to the probability A is false? So again, this part here is false is here. Multiplied by the probability B is true. Is that the same? That's what we need to see in the second test. So we know from our formula sheet that we were looking at that the probability that A is false and B is true, that probability is 30%. And the probability A is false is 60%. And the probability that B is true is 50%. So then we put in the 30% right here on the left side. We put in this 0.6 here for probability A is false and this 0.5 for probability B is true. So this side evaluates to 30%, 0.3. And the left side is 0.3, so 0.3 equals 0.3. Thus, the probability A is false and B is true is equal to the probability A is false multiplied by the probability that B is true. So thus the second test was passed and the independence of A and B has been upheld so far. So we're tracking along to see if the third test is true, because we found that the probability A is false and B is true is equal to the probability A is false multiplied by the probability B is true. 0.3 equals 0.3. So we were really happy with that. We were really, really happy, and I have a little green star. So now we're going on to the third test. Is the probability A is true and B is false, is that equal to the probability A is true multiplied by the probability that B is false? So the A is true part comes here, B is false part comes here, and we're seeing if they equal. So if this one doesn't pass, then again we can say that they're not independent. So from our table, we know that the probability that A is true and B is false is 20%, and the probability A is true and the probability A is true is 0.4 and the probability B is false is 50%. So we know these values from our table. So we put in the 0.2 here for the probability A is true and B is false. And since probability A is true is 40%, we put that in here. And probability B is false is 50%. So this evaluates to 0.2. So 0.2 equals 0.2. So that is great. Thus, the probability A is true and B is false equals the probability A is true multiplied by the probability B is false. So even the third test was evaluated to true and it was passed. So independence is upheld so far. And we just have this last test. Is the probability that both A and B are true? A is true and B is true. Is that equal to the probability A is true multiplied by the probability B is true? So it's a true for A, true for B. So we know that the probability A is true and B is true is 20%, again from our table, and that A has a 40% probability of being true and B has a 50% probability of being true. So the probability A is true and B is true is 0.2 is 20%, and then we take this 40% right here for probability A is true, and we take the 50% for probability B is true and we put those together and multiply those out and get 20%. 20% equals 20%. Thus, probability A is true and B is true is therefore equal to the probability that A is true multiplied by the probability that B is true. So this fourth test is also passed. So all four tests were true, evaluated as passing. So since all four tests were passed, A is independent of B. So all four tests passed, Yangshi. All four tests passed, Yangshi. Thus, A is independent of B. Please note that we needed all four of these statements to be true for A to be independent of B. The same thing as B being independent of A, or just A and B being independent. We needed all four of these statements to be true. And indeed, that's what we found. We found that all four of these statements were true. So what we found from our analysis is this. Indeed, each and every single one of these passed. So we are really happy to say that, all four combinations are equal. They yield equality. So if only one or two or three of them passed, then we cannot say that A and B are independent. But if all four of them pass, then we can say that A and B are indeed independent of each other. So we needed all four of these to pass. So if we're given this joint probability table, so in this example here, and we're asked, is A independent of B? The answer is yes. Please note that A and B are independent. A is independent of B, or equivalently, B is independent of A. So that's how you do this analysis of looking for independence between random variables. Thus, in this video, we learned how to see if two random variables like A and B are independent, Yangshi. But what about conditioning? Like, how can we find if A and B are independent given some random variable like C? That's what I'm going to talk about in another video, but here I'm just talking about how we can see if two random variables are independent or not. So in this example, how can we see if me and Yangshi are independent? Well, I'm going to put them on the bed and see how they act. Yangshi has seen the light and he really likes it. So he's very curious as to this light toy here. So thank you guys for watching, and please let me know if you have any questions at all. I'm Sanya Kotter and I'm happy to help. And yeah, please subscribe to my channel for more updates, and please stay tuned to the next videos about kind of how you can see if A and B are independent given C, for instance, conditioning. So it's called conditional independence. So I hope that that video will also make sense, but that this video gave you some strong background to go into that video with.